Hi everyone! Today we are doing a second part of our revision for Coordinated Sciences Physics for this year, and this time the topic is waves, part 2. The reason why I'm choosing mechanics as part 1 and part 2 as waves is of course because these two topics are one of the hardest topics that students have problems with. Okay, so we are starting with waves, light, and sound. First, we would like to talk about general wave properties. General wave properties means to be able to define what a wave is. Wave is a transfer of energy and not a transfer of matter. That is something that is very important in the definition of a wave. So it's a transfer of energy and not matter from one point to another, which equals wave motion or wave propagation. Wave motion or propagation. Waves propagate. They do not necessarily move because the points are vibrating or oscillating at fixed positions in a horizontal context. We have two different types of waves in way of their propagation. The waves we are talking about here are transverse waves. Transverse waves, and this is usually what we consider a wave, what we usually see as a wave. Here we have some characteristics of a wave that give us more information about what a wave is, how does it look like, and so on. So this is a transverse wave. We will see what that is soon. But here we can see that we have highest points are called crests and the lowest points are called throws. Height of the wave from the middle point, from a neutral point, is amplitude. It is not correct to say that a height of a wave from its deepest to its highest point is a wavelength. It's a amplitude. It is actually 2 times the amplitude. So please do not forget that this is amplitude, height, or depth for that matter, or depth of the wave. This is also amplitude from the neutral point. From the neutral point. Next thing, which helps us describe a wave, is its wavelength. Wavelength has an interesting symbol called lambda. Lambda is a Greek letter as well. We really like Greek letters in physics. And is a distance between two corresponding points in a wave. And in this context, this is between two crests. It can also be between two throws. This would also be lambda. And also it can be between this point and this point, as you see, which are corresponding point, because this is a full oscillation of a wave. Okay, so now when we remember this, we will continue further. Wave fronts is another word that we use, which is waves pictured from above. Basically, wave front is a boundary that determines the end of one wave and the beginning of a different wave. So one wave front is between two wave fronts you have one wave. Or we can say that one wave front represents one wave, however you would like. Technically, if you would be looking at this, distance between two wave fronts would be equal to the wavelength. Frequency is a number of waves per second. This is the reason why frequency is in hertz. Frequency here, you remember in the middle parentheses we usually put the units. So this would be second to the power of -1, which would be an SI unit, but it has its own name, which is hertz. Do not forget that it is second, 1 divided by second, or second to the power of -1. The formula that determines the speed of wave is this one that we see here. I'm going to draw it, put it in a triangle so it is easier for us to remember. V goes up, F frequency, and lambda, which is wavelength. Wavelength, of course, is in meters because wavelength is a part or type of a length, and speed is meter over second. Now, Transverse waves, we just talked about them. These are types of waves in a wave of their propagation. Do not confuse that with types of waves in a context of mechanical and electromagnetic waves. We will talk about that as well. For now, we are talking about the waves in a way they are propagating or traveling through the matter, or it doesn't have to be even through the matter. Transverse waves, vibrations are perpendicular, or at a right angle to the energy transfer. Okay, so the direction of the vibration is perpendicular to the direction of energy transfer. You see it is traveling from left to right, but the particle, is vibrating up and down. So that's very important. Vibration of the particle of the source, however you want, that is transferring that wave through the matter or through the space is perpendicular, it's up and down. For example, transverse wave is light. It is also water waves are usually transverse. Longitudinal waves, vibration is parallel to the energy transfer. Vibration of the particles is parallel to the energy transfer. Here we see that the direction of the vibration is left to right. And also the direction of movement is from left to right, but either way they are parallel. We're going to also talk about characteristics of the longitudinal wave soon enough, because we're going to talk about the same way how we have crest and throws in transverse waves, here we have something similar. But first now we will continue with wave effects that we can see in waves. So now it would be very good to say that we are talking about mechanical waves. Mechanical waves means the waves that need matter to propagate through that matter medium. It can be water, it can be air, it can be anything else. But here in this context, I just want to say that because soon enough we're going to talk about light, and light is not a mechanical wave. It's electromagnetic wave, and it doesn't need medium to propagate. Now, these wave effects can be seen both in mechanical and light waves, but there are some differences here. In general, let's now learn about reflection. Reflection at plane surface. Here, for example, we will have the so-called angle of incidence, and we will have angle of reflection. And we have a barrier here. This is a plane barrier, which means it's a barrier that is flat, right? There is no curve here. And we must not forget that we have a normal, which is a line which is perpendicular to the barrier. Never forget this, knowing that this is a normal. Now, please do not forget that when you are looking at the angle of incidence coming into that barrier and angle of reflection, they are observed according to the normal. Not here, okay? Not this side here. According to the normal, both angle of incidence and angle of reflection. And in reflection, this angle of incidence has to be equal to the angle of reflection. This is the rule of reflection. Refraction, FR, is due to difference in speed. When waves enter a new medium, it changes speed. So the wavelength either goes up or it goes down depending on what type of medium it goes in and from which type of medium. And also there is change in direction if we have change in angle. If this was straight, then we wouldn't have change in direction, just FYI. This is related to if the incident ray comes at an angle. Now here we have a move from deeper water to shallow water, and we have slower, so basically our water speed of our waves goes from faster to slower speed. So here we see that the wavelength decreases as well as we go from deep water to shallow water. Diffraction. Diffraction is another wave effect. Waves pass through a narrow gap. It can be a slit, it can be a gap, it can be a very small obstacle. But in the context of your level of physics, it is a narrow gap. And then what happens with the waves? They spread out. They spread out while wavelength remains constant. It is feasible when gap is smaller than the wavelength. Look at here. In this here context, here we have, this would be the length of the gap, width of the gap. And here this would be wavelength. As you can see, this the width of the gap is way bigger than the wavelength. This is what causes the diffraction effect to occur only slightly at the corners. However, when the wavelength is bigger than the gap size, we can see bigger effects of diffraction. Therefore, we have more curvature. However, please be careful when you draw this, that the wavelength that you approximately have here is the same as the wavelength here. Do not draw it like this, you know? Try to kind of understand that this is also a very important feature of wavelength. So wavelength, which is way smaller than the gap size, we will not really have the effect of diffraction. Ripple tank is a device, an instrument that we use in physics to demonstrate different types of wave effects. It has a light source because we are usually observing what is happening beneath on the table or on the paper we might put beneath the ripple tank. So we need a light source, so therefore that we see these wave fronts. We have, of course, water, and we have wooden bar supported by elastic band. And usually we also have some type of motor that is oscillating up and down this wooden bar. And this wooden bar can produce different types of waves of different types of wavelengths and frequencies. As well, we can put here different types of obstacles and then also see different types of wave effects such as reflection, refraction, and diffraction. Okay, please know the difference between three of these. Now we're coming to light. Light is a bit different than the waves we talked about now. But we are now again talking about reflection and refraction, because the reflection and refraction that happen in the mechanical waves also happen in light waves. And light waves is a electromagnetic wave. And light is also a transverse wave, because all of the electromagnetic waves are transverse waves, which means they go like this, right? Very important thing to remember here is that light doesn't need a medium to propagate. However, it can propagate in any transparent medium such as water and air. Again, we have a normal here. Never forget this normal. Oftentimes they give you a question and they're trying to trick you by asking what this angle is. Be aware that the only relevant angle that we need to consider is the one that is according to the normal. Again, we have an incident ray and we have a reflected ray. And in this plane mirror, again, we will have that incident and reflected angle are the same. In a mirror, if we have an object that is put in front of a plane mirror, the mirror that is flat, as I say, we will have incident ray, which are, as you see, coming here, and they are being reflected at same angles. Okay. And then in the extension of the reflected rays, in the extension of these reflected rays, we will have an image. This is the way we draw it. So optical image is of the same size as object, is of the same distance behind mirror. So you see the distance here and the distance here will be the same. And also directly in line with the object. So it's indirectly in line with the object. This also describes our experience of seeing ourselves in the mirror. Refraction is a bit different here because we have change of the medium, which then results in change of speed. Delta is change. Delta, again, Greek letter, means change. Again, we have angle of incidence. We have a normal here, as we see. And then we have slight refraction, where we are going from optically less dense material to a more dense material, and therefore we have refraction towards the normal, so our angle gets decreased. And then when it exits this glass, it then continues with the previous angle, the one that was incidence angle at the end. So here light bends at a boundary between two optical mediums. Here it bends towards the normal because it becomes smaller. Here bends away from the normal because we have less dense medium. Here, if we are wondering how much a certain medium will refract, therefore bend towards normal, a ray of light when light is entering it, we can use something called refractive index of a material. So that is n equals sine I over sine r. So sine of incident angle divided by sine r. Another way also, this is light in vacuum, speed of the light in vacuum divided by speed of light in medium. It is always bigger than 1 because light in vacuum, which is c, which is 3 times 10 to the power of 8 meters per second, is the fastest speed of light that can be found in nature, because in vacuum there are no particles, and therefore there's nothing to slow down the light. Refraction can be investigated through these different types of slits and particles, and by different glass blocks and varied sizes. We can also, with the ray box, produce a very, very narrow slit, light source, let's say, through which we can then observe all of these things that we just talked about. Total internal reflection. Total internal refraction is something that we use every day without even knowing it. Internet is an optical cables, and almost all of the media in our life is possible because of this. When light travels between media, when it goes from more dense to less dense, usually it goes from less dense to more dense, the one that we've just seen before, but if it goes from more dense medium such as glass or water to a less dense, optically dense medium such as air, most light will be refracted and some light will be internally reflected. So beyond a certain angle, C, which is the critical angle, all light is reflected back into the glass. This might be a bit confusing, but basically knowing that there is such a thing as critical angle, and that critical angle, after that critical angle, there is no more, there is no more refraction, there is also reflection. It is easy to kind of understand how this works. So here we have refraction because it goes up, but at the same time here there will be a small part of reflection. There will be a reflection here as well. There will be a small part which is reflection. And then at the end there will only be reflection. There would be no third. There would be no third ray, in a way. So all of the light will get reflected from the surface of these two mediums, which is, this is air and this is, let's say, glass. Application of total internal reflection is optical fibers. And in optical fibers, this is usually how we draw them. So be careful when you draw this so that internal incidence and reflected ray are the same angle. So basically, however, in an optical fiber, however a light comes in to the cable, it will continue reflecting from the inside surface of the cable without going out. And therefore, we can use it for transferring signal. In medicine, it is possible to see inside of the human body because we cannot look at in the human body just straight. These optical cables can be bent, and because of the total internal reflection, it is possible to see what is happening inside of the body. Thin converging lenses. So we talked about mirrors a bit, but here we have thin converging lenses. We only talk about converging lenses. Converge means that they look like this, right? They look like this, like an almond. in a way. It brings parallel light rays into a focus. This is a feature of converging lenses. So they all go to the focus. Focus is halfway between the center of the that side of the lens. It depends on the curve of the lens. So therefore, if I have a more curved one, will it be more in or more out? So the more I curve it, the more in it will go. It is forming real images from real objects. Real images can be enlarged, they can be same size, they can be diminished. You will see that in a second. They can be upright or it can be inverted. So based on placement of objects from the lens, real images can be projected also onto the screen. This is very important. So here you have all real images depending on where they are. If an object is between a focus and 2f distance from the center, we will see it as a real image which is upside down, which is enlarged, and which is real, can be projected on the screen. In the second one, if we put an object exactly in the 2f, so 2 focus size from the center, it will make us a real image projected on the screen, but it will be inverted, the size will be the same. And in the third object, if we put a third example, if we put an object way after 2f distance, we will have a real image which is inverted and smaller, diminished. Virtual images, for example, magnifying glasses. They have an object closer than focal length. So here, you see, we do not have it anywhere here, right? It is also always after the focal length, in the distance which is more far away than the focal length. Object is closer than focal length, like light rays diverge. They can't form a real image, unlike in the other context where we have conversion. Extended rays backwards, so virtual image. Virtual image is when we have again extended ray. So this ray goes this way, then down. Its extension is backwards. This ray goes straight like this, so its extension is backwards. We have a virtual image which is enlarged and also the same orientation. Electromagnetic spectrum. Shared properties of light is that they are transverse waves. They travel through vacuum at same speed, which is this, 3 times 10 to the power of 8 meters per second. And speed of light in air is similar. Here we have electromagnetic spectrum. We see also that we have lower energy if we have longer wavelength. And I kind of make this easier to remember is by saying that this is basically red, kind of coloring it, let's say, in a red way. And from the other side, coloring it in a blue or purple way, however works for you. So here we have wavelength. So I put wavelength here. What is happening with the wavelength when I go from left to right? The wavelength is going down, right? It's decreasing. Whereas what is happening with the frequency as I'm going from left to right, it is going up. So that's something that I need to remember. I need to also remember that wavelength and frequency are inversely proportional. When one is going up, the other is going down, and reverse. In this context, when we are going from longer wavelength from red to blue. Here we see also that we have radio waves going from left to right, and we need to know this. Radio waves, microwaves, infrared, visible light, which is a very tiny part of the electromagnetic spectrum, ultraviolet, X-rays, and gamma rays. And we need to kind of know the use of each of these. So radio waves, they are used for TV and radio. They are used for long-range communication. Reason because they can be reflected from the Earth's atmosphere. So inside of it's similar to total internal reflection. Microwaves are used for satellite communication. Reason because they can penetrate Earth's atmosphere, because they have higher frequency than the radio waves and shorter wavelength. Infrared are used for optical fiber communication. Reason because they can undergo total internal reflection. Visible light is used for taking photos and videos. Reason cameras are set up to detect visible light although there are some cameras that, of course, they can detect infrared, ultraviolet, or different types of lights. Ultraviolet is used for detecting security ink, for example. Reason because it fluoresces with ultraviolet lighting. For example, suntan. Suntan beds are UV. This is also one of the reasons we are seeing as we're going from left to the right, we have a higher and higher frequency. This also kind of tells us that the higher frequency is more damaging towards us. Ultraviolet is not a great part of electromagnetic spectrum for our skin. Now, X-rays are used to photograph bones for radiography, for X-ray scans, and for Röntgen, because X-rays can penetrate soft tissue but not bone. And gamma rays are used to sterilize medical tools because they kill bacteria. Infrared is used in electrical appliances, in TV remote controls, in intruder alarms. We would like to know kind of a few examples. Safety issues. So here from X-rays and gamma rays, we have ionizing radiation. Not all radiation is ionizing. We must not forget that. For example, what can be some safety issues here? Microwaves have high levels of, how should I say, microwaves or high levels of microwaves. Now we will talk about safety issues a bit. Microwaves, there is high levels of microwaves are not very good because of heating of internal organs. But microwaves are not radioactive. Please do not think this. X-rays, gamma and UV are ionizing. Going from UV, then X-rays, then gamma rays, and their ionizing effect is increasing. They can harm or kill living cells, and they can cause genetic mutations which can lead to cancer. UV, sun, or tanning lamps ages skin prematurely and increases risk of skin cancer. Now we are coming to the last part, which is sound. Now, do we remember what type of sound, what type of wave is sound? Sound, in the context of its propagation, is a longitudinal wave. However, it is also a mechanical wave that we need, that propagates via some type of medium, some type of matter. It cannot exist in a vacuum. Now here we have direction of vibration, and we're going to talk about a bit more about longitudinal waves now, and the direction of energy transfer. You've just seen this. Sound waves are vibrating molecules, longitudinal waves consisting of so-called compressions and refractions. Sound waves are also pressure waves. And types of longitudinal waves in, for example, earthquakes, longitudinal waves are P waves, whereas seismic waves are transverse waves. These are some things also that we can remember. Here, for example, we have an example of, this is a sound fork, tuning fork. And we can also see here that we have these compressions and rarefactions. Sometimes they ask you to figure out what the wavelength is. And we will go from the middle of one compression to the middle of a different next compression. And the distance between these will be wavelength. Also, I can go from the middle of one rarefaction to the middle of different rarefaction. And this should be the same value. So you can do both of these. Or what would be the best is to take a middle of one compression and a middle of few compressions after, and then calculate this, say what the value is. So this is 1, 2, 3, 4, and then divided by 4. The bigger the better here in this context, and then divided by more. Our error is going to get smaller. Here we are talking now about different types of pitch and different types of frequency. Look at this. Audible range for human ear, healthy human ear, is between 20 and 20,000 hertz. Just because people can just hear in this range doesn't mean that, for example, dolphins or dogs cannot hear in different ranges. This is the reason why they sometimes calculate in, they are communicating in different levels of frequency. So low frequency and pitch, for example, is infrasound. Range of human hearing is 20 to 20,000 hertz. So something below 20 hertz will be infrasound, infra. High frequency will be ultrasound, high frequency and high pitch. And here we are kind of also learning about differences between frequency and pitch. Let's remember this very shortly. Frequency is describing pitch. So high frequency, which will mean a higher pitch sound, whereas amplitude is loudness. So the louder the sound, this means it will have a higher amplitude. Let me give an example here because I do not see it here. Yes, let me give an example. If I have two waves, one is going to be like this, and one will be like this. I'm trying to be careful here to put the wavelength to be almost the same between these two waves, 1 and 2. Which one of these waves has a higher amplitude, or rather which one of these waves is louder? I'm going to also put the base here so you can see what amplitude is. Amplitude is this, right? And this. So of course, because their frequencies are the same, this will be louder and this will be quieter. Okay, now let's do another example. Let's compare higher pitch and lower pitch sound. Here I'm gonna have the same amplitude, but this time I'm going to have different frequency, and we can see this, right? So if this is 1, this is 2, the one above will have higher pitch and lower pitch. Let's not forget this. Other things that we need to know about sound. Audible range for a healthy human ear is 20 to 20,000 hertz or 20 kilohertz. 20 kilohertz. Sound waves need medium to travel through. They can't travel in vacuum because there's no molecules. This is the speed of speed of sound in different medium. For example, in gas it is 350 meters per second, but you can see the more denser the medium, liquid is more dense than gas and solid is more dense than liquid, we will have higher speeds. This is something that sometimes is not very intuitive in the context of our everyday life, so please do not forget this. In liquid, the average speed of sound is 1,500 meter over second, almost 5 times the speed of one in gas. In air, in solid, it's even higher than this. So speed of light is higher in denser materials. As I said, loudness is proportional to amplitude and pitch is proportional to frequency. Louder, greater amplitude, higher, greater frequency. Sound can be reflected, like always, which results in something called an echo. So here, if we want to do an experiment to determine speed of light, we will have to have someone a set amount of, set distance away from us, and we would have to have it clapped. We would then measure, we would see when the clap happens, and then we would measure when we hear the clap. This is also something related to like thunder, when we hear thunder and when we see lightning, there can be certain distance between two of these because, of course, light travels way faster than sound. Therefore, when the difference between lightning and thunder is very, very short, this means that it is closer to us, depending on when these distance differences are very big. So to measure distance, we have trundle wheel, we bang wooden blocks together, we have a stopwatch, start when banging and stop when hearing a sound. This would be very hard to measure like this, but we repeat, of course, multiple times and take time the average and we calculate the speed. Now echo, we can do this better maybe in echo, because in echo we will have distance from us to the wall or to some type of wall and then back also. So please do not forget to calculate the speed for echo. This usually would be 2D. Be careful about this. Do not forget that the distance will be doubled in this context. So this is it related to waves. I hope it will be useful for you to revise, and see you in the next video.